All right. Hello, everyone. My name is Antonio Garcia-Dominguez, and I'm going to be presenting this work that Nelly and I did with Owen as part of his PhD on automated collection of runtime provenance. So that's a bit different to, for instance, the OpenCISA presentation was more on, say, why did you do this while you were designing the module? This is more what happens when you are essentially running a system on top of a module. Okay, so I'll talk a little bit about why this particular work. So essentially, we are interested, and especially this came from Nelly's side of the research, on systems that are self-adaptive. So the idea is that the system is somehow monitoring, has a model of itself, and is monitoring its own goals, how those are going, its internal parameters, and so on. And then based on that, it will reconfigure itself in some way, or change the way in which it's operating, right? So that's it's good in that it can adapt to the environment, but it also makes things a bit harder to explain. So when it's doing something strange, you say, well, why was it doing that? What did it see? What did it notice before it started doing that very strange thing? So we had a previous paper published in SAM, actually, and later extended in IST, where what we did is to instrument that model that the system is using during its own execution to catch whenever it changed, where to catch as part of which activity that change or that also access to the model happened, and who was running that activity, right? So we could kind of track what was going on in the model. But we had one limitation, which some of the reviewers observed, which was that we're pretty much limited to models in EMF, e-objects, right? So we were limited to a very specific technology. So this paper is a little bit about trying to lift that restriction that we have. So to talk a bit about provenance and the way that we model provenance in this work. So we understand it's all the information that explains how something came to be. And particularly, we're using this W3C data model for provenance, where we essentially divide things into agents who are performing activities that are producing and modifying and reading entities, right? We have this kind of triple here with different kinds of edges that can happen, right? So what we actually do as part of while you're running the system is we essentially create a provenance graph where the different parts of your module are the entities, and the things that are going on in the system are the activities, and the things that are running those activities are the agents. So the way that Cronista works is you've got Cronista, this system here, and you've got your system being observed. And what we do is in each of the agents of the system, we add observers, and they kind of latch on to your runtime model. And whenever you're reading some part of the model or you're modifying some part of the model, they send events, they send messages to a message queue in Cronista, which has a curator that is going to build up that provenance graph that you saw before. Okay. So that we have some reusable components there. So the curator is always the same regardless of which system, right? The bit that tends to be specific to the system is more the observer, because that has to, as I say, latch onto your model. So if you wanted to use Cronista in your system, there were generally 3 stages that you had to follow. The first stage was to add, kind of identify the agents in your system. So in our case, we essentially considered each execution thread to be its own agent. Okay, in case you had a multi-threaded system, you had to mark out the activities in the system, and we kind of wanted to decouple them from, say, specific functions or classes in your system, because actually, we wanted to essentially represent activities as the more almost business level things that are going on in your system, and not so much that you're running this particular function or that particular function, right? So you may have if say your system is following the usual feedback loop, where you are monitoring the current situation, analyzing what is going on, coming up with a plan, and executing the plan, you could actually outline those activities in the system. And then finally, you will need to instrument the accesses to the runtime model, right? So say that that's a difference that we have. We say, things like OpenCSR, because, as far as I understood, felt to me more like, it's more like a design model, as far as I can tell, whereas we're more considering runtime models, right? So the system has a model inside it, and which kind of goes with the keynote actually that we had with, the program as it runs, it builds a model. So it's that model that we're talking about, right? The system as it runs, it's operating on that model, and that's the one that we want to instrument. Now, obviously, this process is a bit iterative. The first time you apply Cronista to the system, you'll get the provenance graph in a certain way, and it might not be exactly what you expected, or it might be not have the information you expect, and you may do a little bit of iteration. For instance, breaking up your activities to make them more fine-grained or less fine-grained, and so on. So if you wanted to do this for EMF, which was the original version of Cronista, as I said, we would add, for each thread of execution, we would add an observer. Then the activity scopes, we actually represent them in as try with resource blocks in Java. So essentially say this block of code with this region of the code is this activity particularly. And you could do things like nesting activities, right? You can have sub-activities in there as well. And then you'd have to change the code generator from EMF to use the model instrumentation that came with Cronista, so that any access to the model or any modification of the model will be sent over to the curator so that it would expand this provenance graph. So what we essentially did, we added a little bit of code into the system through the code generator in EMF, and as I say, that produced those messages. Now, as I said before, the issue that we had was if you're not using EMF, or if you cannot really change the way you're generating the code because you already have some of your own customizations in EMF, how would you be able to apply Cronista, right? So people may be using other modeling frameworks that are not EMF, or you could just not use any modeling framework per se. You could just have plain Java objects, right? Or plain objects in your modeling in your system. Of course, those plain old Java objects, they will have to, have some meaning behind it, right? There should be some meaningful representation of what your system is thinking about itself, really. So in general, if we want to add this code to the system, that means having a lot of little bits of code all over the place, right? And that's what typically people understand as a cross-cutting concern. And aspect-oriented programming has been a very commonly used tool to do this, to implement these cross-cutting concerns. Aspect-J is one such tool, which is heavily used by the Java community. And the basic idea of an aspect is you have some advices and you have some point cuts. So point cuts are ways to point out to specific parts in your code, specific locations in your code. So, before and after this method, or before or after this or that happens in the code. And then the advices are the bits of code that you want to insert in those places, right? So what we did was to try to essentially replicate what we used to do with EMF models in a more general way with Aspect-J. And what we did first is we tried reproducing what we had on an EMF-based runtime model. And then we tried to apply the same thing, but on a third-party system that wasn't using any modeling framework, right? So we thought, let's go to the extreme case. There is no modeling framework at all. And let's see what happens. So first, the bit that is related to EMF. So what we had originally, as I said before, we were customizing the EMF code. So EMF has this support, what are called dynamic features, which means that any getting or setting of those features or attributes and properties in the model objects would go through those eDynamic get and set methods. And we essentially overrode those basic methods to catch those calls and send over a message to the observer, right? To the curator to populate the graph. So that was reasonably easy to reproduce in Aspect-J. We essentially provided it with those point cuts that we said Well, when e-dynamic get is being called within a class that has a particular Java notation, okay, we can add some extra bit of code, which is equivalent to what we used to do. And when e-dynamic set is about to be called, again, if the class has that notation, then that also happens as well, right? So what you essentially have to do to instrument your model, EMF model, is just add annotations to those classes that you have, which is very common in Java. People are used to like Spring Boot and all these things, just dropping annotations in there. And the good thing is that also, even if you were to regenerate the code, we checked, and the EMF code generator is going to preserve the annotations, right? So you're not going to lose that little bit of customization that you're going to do. One thing that we do have is we have something called the model inspector, which is called by the advice, which is going to collect the ID of the element. So yeah, we can actually identify when you're modifying, if you're reading and then changing a part of the model. So you can identify that it was the same part of the model. So that's something that the model inspector does. And it may be specific to the model because different models may identify elements in different ways, right? So that's something that we kind of split off. And then also bits of the element state, which is something more reusable because that APIs in EMF to generally get the value of a particular part of the model. Now, we applied this approach to the original simulation that we had from the SAM 2020 paper. So the original case study that we had was a traffic simulation with the Sumo simulator. So we have essentially these two intersections that have traffic lights, simulated traffic lights on all sides. And they essentially, it's a self-adaptive system which controls for how long do you keep the different signals based on how many vehicles you have on top of these pressure sensors, which are those blue bits that you see over there. Those are actually detecting how many cars are on top of them, right? So, we essentially did the same thing. We had the simulation run, we collected what was going on, and we also tried the same approach where we introduced a fault in the control logic for the traffic lights, which kind of simulated somebody forgetting to write a particular Boolean condition correctly. And we were able to catch exactly the same issue with this new method of instrumentation, right? So essentially, from a provenance graph point of view, this new method is equivalent to the previous one. We ran some numbers to see what kind of overheads that produced. So in terms of simulation time, there wasn't really that much impact. In terms of memory resources, we actually noticed that they use a bit more memory with aspects. For data, it also sent a bit more data over the network to the graph storage, essentially. And the size of the graph was slightly bigger. But one bit that, for instance, we may also explain this difference was the fact that in this case, there's some randomness to the simulation. And for this first case, we weren't quite controlling that randomness. So part of it may be due to aspects, part of it may be due to just the stochastic nature of the simulation, right? One thing that we also did that I did not mention here is another thing you can do, because we're using annotations on classes, is that we weren't able to do before, is you can actually pick which parts of the model you want to watch and which ones you don't, because you can decide to apply or not apply the annotation to a particular part of the model. So you say, I actually don't care about the updates or the accesses to this part of the model, you just not annotate that one. And that's the bits that you see the green bars. So the green bars are for when I'm only doing partial aspects. So I'm only covering some of the model and not the whole model. So that does reduce resource usage a bit, but not really that much in the first place, to be honest. Because most of the cost of keeping the graph is just the base cost of just starting a graph database, which has a base cost. So it didn't really change things that much for us. Okay, so I'll just, I already said these things. I'm just going to skip along to the next one. Now for plain Java models, right? So the next thing that we wanted to do was to say, okay, imagine you're not using EMF at all. You're just using plain Java objects. What do you do, right? Now, the thing is, obviously, I think we talk about that in the keynote this morning, is that essentially, more disciplined ways to do data models in Java and less disciplined ways to do, those data models. So for instance, if you have something where you have a bit more better structure, where you say you have these Java beans where, you only have the bits are really relevant to the module and they all have uniform getters and setters and ways to access those values. Then it's pretty easy to get to with things like aspects, because they're quite consistent, right? But if you have something where some of it is relevant to the model, some of it is not relevant to the model, method names all over the place and so on, it can be actually quite tricky, right? So this is something that we kind of get for free with EMF, but once you stop, a modeling framework that makes things a bit more consistent. But once you go out of that, who knows, right? The different people may write code in very different ways with better quality or less quality. So depending on that, right, the way that we would have to apply the aspects would change, because if you have something very consistent, this idea of the Java beans, actually the way we implemented this in AspectJ, if it's just your standard Java bean with your getters and your setters and very consistent, and all the information in that class is part of the model, you can just do the same thing we did in EMF. You can say, this is part of the model, observe it, please. But if you have something less structured, where only some of the fields really matter, only some of the methods, only some of the interactions in those methods really matter, now you have to go and, in a more fine-grained way, say, this matters, this doesn't matter, this matters, this doesn't matter, right? And in that case, you actually have to apply to different annotations. So you have to say if a particular field is part of that model that you want to watch, and if a particular method has interactions which you actually want to watch as well, right? You have to be a lot more fine-grained with respect to that. And also the bit that we said about the inspector, about object identifiers, for instance, and getting the state, that can also be quite tricky, because again, because it's just plain Java objects, they don't really have persistent identifiers by themselves naturally, right? You have to kind of either sort of re-implement that bit that you may get with a modeling framework yourself, or you kind of try to work around by using, say, the unique-ish identifiers you get from Java, right? The kind of hash code kind of thing that you get for free, which is not perfect, but if it's the only thing you have, well, you have to use that as much as you can. So we basically said, let's try to use this. We searched GitHub for a Java project that was developed by somebody else. So because the previous simulation we developed kind of with a runtime model in mind, we said, let's just pick something that some random person developed that was plain Java objects. And because, again, we don't have access to all the facilities of, say, thread-safe model repositories that you get from modeling frameworks, let's go for something single-threaded that had a runtime model that people could kind of understand, and it had a little bit of its own decision-making that you could track with provenance and say, why did you decide to do this? And we chose something pretty simple, essentially just a little program that plays checkers by itself. And it has this typical alpha beta tree search based decision making, where it's trying to pick the best move that is not going to let the opponent do something too bad to itself. So we have those very simple 4 Java classes with the main class. The heuristic was implementing the state of the game and the available moves. So a runtime model was that kind of tree of different moves and the game board and so on. And we have links on that slide, to the original system and to our instrumented version. So in that one, we had some challenges. So, obviously one part was the model wasn't implemented in the most cleanest of ways. So it took some time to actually understand what the author intended the code to do. So, it took some time to essentially instrument the system with the activities that were going on in the system. And we also have to be careful about selecting which bits we actually wanted to observe or not, because otherwise we could just flood the creator with many irrelevant events, right? We also, more for the experiments, we had to make executions repeatable to measure resource usage for repeatability. And then we thought about some ways that we could use on the provenance graph to kind of try it and see what kind of things we could find out. So we took quite a few iterations to get this right. That's probably where most of the time in this paper went, to just clean up that thing that didn't have a clean model in the first place, to be honest. So we started with high-level activities, like, let's see what happens in a player's turn. let's try to find the objects and the fields that have meaningful representation of the game state, so that runtime model. And then we run the game, check the provenance graph, see if it really kind of had a logical thread of evidence over what happened in that runtime model. And if not, we actually had to tweak that model a little bit before we, it kind of made sense in the provenance graph. We ran some experiments in terms of the overhead that we had. So in terms of system speed, didn't really have any impact. Memory consumption went up quite a bit because we do have to keep track of the different versions of the objects and so on. So it was more like a 1 megabyte. It went up to 10 megabytes or something like that. Provenance data wasn't really that much, to be honest. More on the order. This is for like a single game of checkers, so more like 16 megabytes or something like that. And the provenance graph, well, this is more the overall size in memory of the provenance graph. So this is Janus graph. And if you just start the Janus graph, it's already 700 megabytes because it's a full-on graph database, right? So it's more this difference is the actual size of the graph, this difference that you see here between not using provenance at all and using provenance. So there was some overheads, but it wasn't so much the cost. It was more the just the effort of cleaning the that data model. And once you do that, then you can actually write a graph query like this one. It's a Tinkerbell-based graph query where you try and find the entity that represents moves. Then you find the activity that generated it. You find the entity it used to pick the best move. And you find out that it was generated by this other activity. And there's certain information that you can get about how many possible moves it had to choose from, right? And in general, what we found was, you can certainly use aspect-oriented programming to add this automated generation of a provenance graph. And the overheads weren't really that different to your typical EMF code generation. And you can use Cronista for plain old Java objects, but then the problem is, was the original programmer really thinking in terms of a runtime model, or did he just want to get the program to run, but they didn't really try to make something clean that you could really treat as a proper model? And most likely this approach could work with other modeling frameworks, so long as they have like a consistent coding scheme, kind of like what we did with Java Beans. And I believe that's pretty much it. Thank you.